as well. All right, so we're starting off, this is mechanics number 5. Mechanics number 5 is all about graphs. And we're going to start seeing graphs hopefully different than you've done before. Holler loud if you have questions, because I talk loud and I can't even hear over myself. All right, so first we start, we're going to be looking at 3 different graphs. We have distance time graphs. So we have distance time graphs over up here. Distance time graph. And then we'll move from there. But starting out with a distance time graph. The first thing we want to start talking about is how to interpret a line on it. What does the line mean? If we have a curve, what does the curve mean? All right, and in order to do this, what we start changing up is the idea of slope. So we're going to look at this concept of slope. And what's the easy definition of slope as far as you guys know? How do you do it?
Rise over run.
Rise over run. Okay? So let's think about this, and we'll use the concept of rise over run. I'm just trying to get a little bit better light on the situation here. Rise over run. What are the units of distance? Meters, correct? What are the units of time? Seconds. So when we say slope equals rise over run, what does that mean? Well, put the units in. What's the units of rise here?
Meters.
Meters. Beautiful. What's the units of run?
Seconds.
And what is a meter per second? A unit of what?
Acceleration.
Not acceleration.
Oh, velocity.
Velocity, right? Rise over run gives you velocity. So a distance time graph, what is slope the same thing as?
Velocity.
Velocity. So tell me, what's the velocity doing here? Staying the same or changing?
And the same.
Staying the same. How do you know?
It's a straight line.
Right, the slope is not changing, the velocity can't be changing. What's the velocity doing on the blue line?
Increasing.
The velocity is increasing. How do you know? The slope's increasing, right? So when you take velocity and slope and you make them interchangeable, suddenly you can see inside a graph much, much better. So real key of how we're going to start thinking about graphs is we're going to use slope all the time. Now when you first did your silly lab, by the way, I want all the silly labs handed in as soon as you could get it, or the labs 1 and 2. I put everything online about how to do them. So if you have any needs, talk to me on Schoology, but try to get those up and running.
I think I said that to you.
Okay, when you look at like your 3 silly walks, which was the fastest? Now think about slope. Which is the steepest slope? A, B, or C. So which is the steepest slope there?
A.
A, right? And hopefully you can see into a distance time graph a little bit easier than you could before. That's the point. The other concept that we often will talk about with graphs is the area under the curve. And with all things, the units tell you what the meaning is, or even if it has any meaning. So let's look at the area under the curve here. All right, so if I were to mark off the area under the curve, what formula do we use for area under the curve? And I recognize it's a triangle, so we use 1/2 base times height, right? Well, on this, we're not looking for a number, so just base times height gives you the meaning of it. So what's the units of base? Seconds. What's the unit of height? Meters. So when you take the area under the curve, you have base times height, and that equals a meter second. And what is a meter second?
Nothing.
It has no meaning. It has no meaning. The whole point of this is that whether the slope has meaning or whether the area under the curve has meaning is not to be ever memorized. You figure it out. And this really turns into important because we're going to do graphs like crazy now. Then when we get into other things, we're not really going to do graphs much for a while. But then suddenly, 2 months later, on a test, I'm going to hit you with a whole bunch of graphs. If you've memorized this stuff and haven't learned how to figure it out on the fly, this is devastating. But if you've learned how to figure it out on the fly 5 years from now, you won't have any trouble with it because you go, well, okay, I'm not supposed to memorize anyway. You use the units to figure out what meaning it has. So we'll continue on graphs and we'll look at that with the same idea for the next one. So the next graph is a velocity time graph. So without me doing anything else, take a second, think about what's the slope of a velocity time graph. I'll give you a second, maybe 2. So you do rise over run, look at what the units do, so what do you come up with? What's a unit? What's that?
Meters per second squared.
Meters per second squared. So the slope on a VT graph equals what? What's meters per second squared a unit of?
Acceleration.
Acceleration. So the slope here, okay, don't even have to do it for you. Rise over run, well, I'll do it anyway. Meters over seconds, right? This is seconds over 1. If you want to get rid of it, you multiply by its reciprocal, so you multiply this by its reciprocal. That's meters per second squared, right? So the slope of a velocity time graph is acceleration. Is this showing acceleration?
Yes.
Yes, there's a slope here. Is the acceleration changing?
No.
No, it's not. How would I represent zero acceleration?
Constant velocity.
Okay, but how would I represent it on the graph? Now, you kind of did just say it, but
It would be a horizontal line.
Why? What's the slope of a horizontal line? Zero, so zero acceleration. So when you look at it that way, now you can look at it and say, like, just keep your velocity constant. Yeah, okay, but we're looking at it with slope. And it gives you an insight, I think you would agree, that is kind of useful. Okay, now, for this graph, now what's area under the curve here? Take a second. Go ahead. So what's the area under the curve going to mean?
Distance.
Distance.
In meters.
Right? Meters per second times second. The seconds cancel. You're left with distance. Really, in this case, displacement. And remember, the difference between distance and displacement from point A to point B, I might take a long, long time to get to point B. That's the distance I went. But if I go from point A directly to point B, this is displacement. If I divide displacement over time, that equals velocity. If I divide distance over time, that equals speed. So that's the difference between our use of speed and velocity. You'll find in...
What's the difference between speed and velocity?
What's the difference?
If I'm going a certain speed, wouldn't that mean I'm going at a certain velocity?
It kind of gets into a physicsy thing, and we don't always pay that much attention. Your car speedometer will always give you what your speed is. Now, if you go around a curve and you get back home, and we're using that entire trip, you didn't go anywhere. Your displacement, you started at A, you ended at A. So technically your velocity today is 0. I'm going to end back where I started from. So my velocity, if I use that for the whole problem, my velocity is 0 meters per second. And you can see that's pretty useless in a lot of situations. So you kind of got to have a sense of when to use which.
But if you go in a circle, you still have velocity for that time. So why would you?
Exactly. You have velocity, but in order to say velocity, you're going to have to really break that circle up into a bunch of small chunks. Because if you're using the circle and you start at A and you end up back at A, your velocity is 0. When you run on the track, you get back to where you started. I don't care what the coach says, your velocity was 0. But your coach is not worried about your velocity. Your coach would like you to increase your speed, right?
Why is it that you measure it like that?
It gets into more physicsy stuff that is not really pertinent to what we're talking about. So it's more just defining terms right now. There's a time it becomes important. Right now it's just defining terms, so don't particularly worry about it. But know that on the Regents exam, velocity, that's displacement over time. Speed is your distance over time. So know the difference between them. The way they hit you on the Regents, a lot of times they'll say something like, speed is to distance as velocity is to, they use an analogy. And so speed is to distance as velocity is to displacement. Like that. Whatever. Let's move on from that because that's not really a big deal. I just wanted to put that in right then. All right? So the last graph we have is acceleration over time. All right, now what's the slope of acceleration over time going to be? I can hear you calculating away.
Meters per second cubed.
Meters per second cubed, exactly, meters per second. And what is a meter per second cubed? You got nothing? Me neither.
What is that?
It has no meaning. So the slope, you can't, there's nothing you can really do with the slope here. What it is how your acceleration is changing per second. In high school physics, we're not messing with that. So while it has meaning, it's nothing we're going to be ever messing with. Oh, but wait, what about area under the curve here? Does that have any meaning in this world?
Velocity.
Meters per second squared times seconds. Seconds cancel, so you are indeed absolutely correct. Meters per second is the area under the curve. So the area under the curve will give you what your velocity is. If you accelerate at such and such a rate for this amount of time, there's your velocity. And you can actually pull equations right out of that. So it's pretty useful like that. So let me show you how we do the graphs and how you have to make sure you're trained up to play with the graphs, okay? What you end up with, and it's on the back page of the daily, you see 6 graphs going across the top. The first 3 are for constant velocity. The second 3 are for constant acceleration. So let's do them right here. Constant velocity and constant acceleration. All right, we got that? So, first graph. dt. dt. Good, for constant velocity. Well, what does slope mean in a dt graph?
Velocity.
Velocity. So constant velocity would mean constant. Swap those words. Constant velocity is going to mean constant. Psst, slope and velocity mean the same thing. So constant.
I said slope, but I.
Oh, I'm sorry. I did not hear you. So constant velocity means.
So that's my fault.
No worries. Constant velocity means constant slope. Excellent. All right. Acceleration. With acceleration, what's happening to your velocity all the time? If it's positive acceleration.
Velocity increase.
Your velocity would be increasing. So what else would be increasing? Your slope. So what would an constantly increasing slope look like? Bam! That is how you do that. And looking at slope gives you this insight that makes all this really easy. And that's the point. Now look at a velocity time graph in both cases. Again, what's the slope of a velocity time graph? And don't ever say it quickly. Think about it. Always figure how do you do it. Meters per second time, or meters per second divided by seconds is meters per second squared, which is a unit of acceleration. So, constant velocity, what's your acceleration at constant velocity?
None.
0. So what does a 0 slope look like? Right? Makes it a lot easier. Now you also can look at it from the point of view constant velocity means your velocity is not changing, so that makes sense in that level too. Okay, so constant acceleration, what's the slope of a VT graph?
going up.
But just what's the slope mean on a VT graph again?
Acceleration.
Acceleration. So if we say constant acceleration, we can swap out acceleration and slope, and we mean constant slope. There you go. And by the way, when we say constant acceleration, you would be understandable if you do that. What we always imply is constant non-zero acceleration, okay? Because zero acceleration obviously would be a constant as well. But what we're implying is not a zero acceleration. So for constant acceleration, some non-zero acceleration, there you go. But notice the slope is constant, so that would be a constant acceleration. The last set of graphs, let me tip the camera down and tip you guys down a little bit. So the last set of graphs then is an AT graph, and that's what is the slope of an AT graph? Meters per second squared divided by second. Meters per second cubed, yeah, we have nothing. The slope doesn't help us particularly there. So we have to look at it a different way. Constant velocity, what's your acceleration if your velocity is constant? Zero. So can I accelerate forward and, not at the same time granted, but can I do a forward acceleration or a backward acceleration? In other words, can acceleration be positive or negative? Yeah. So it's reasonable in the middle of acceleration to put a zero, right? So would that be constant velocity? A line right along the zero level of acceleration, indicating no acceleration.
Yes.
Yes, right? So what's my acceleration if I have constant acceleration, constant non-zero acceleration? How would you draw that? Same exact thing, but no zero. Right? Constant acceleration. And notice we're not asking for numbers. We're not fussing over anything. All we want is the lines to indicate that you have an understanding of what these motions look like on these 6 graphs. And that is how you do that. All right? That gets to the idea. Also on this, we have a line of best fit. If we have a series of data, I'm sure you've already met lines of best fit. But if I have a bunch of data, well, how about if I have data points, and on the daily you see I have you doing them. If I have data points going up like that, right? How would I do a line of best fit? Well, you do the line that most fits the data. Is the line supposed to cross all of the dots?
No.
No, it's simply supposed to show the best trend of the data. And you can see what you're really doing, averaging. Right? You're doing a good average of all the data. And because we have so much experimental error induced in almost everything we do, a line of best fit is a really common way to show the trend of things. It's used everywhere in science. Well, I think we have just beaten up graphs, gentlemen. You guys are all right with that?
Yeah.
All right, so that is mechanics number 5. The only thing I would also point out with mechanics number 5 is just a playful thing, and that is the quote there on the front page. It's an important quote. It's a really important quote. Now, I always use this to talk a little bit about why you should be really careful about what you put into your brain. In other words, what you subject yourself to, either entertainment, from video sources, from books, but even in the classes you take, in the things you study, the things that you put into your brain. You do not see the world the way it is. It's not possible for you to see the world the way it is. You see the world the way you are. So if you have filled your brain with some pretty awful stuff through maybe reading way too much Stephen King books or watching weird zombie movies, that's the way you see the world. And you can't help it anymore. That's the way you see the world. If you walk through in your entertainment, if you play first-person shooter games, when you're walking down the hallway, tell me you're not still playing, part of your brain at least, first-person shooter games. You can't help it. It's the way you are.
I don't like imagine that I'm still in a first-person shooter.
When you get grumpy, you do. If you play a lot of first-person shooter games, don't you? And somebody's like making you pretty angry, somewhere in your brain, yeah, you just put a target on them.
No.
No, you wouldn't do that. You can imagine it affects how you see things.
I don't know about that.
I mean, take some time and think about it. I'm not the first person to suggest that this might be so, not even close. I always illuminate this by suggesting that I walk often in the woods at night. And there's a lot of people who think that's kind of like a crazy thing to do. I've lost friends of mine walking at night. Probably 5 or 6 of them I've lost. What happened to them in every case? How did they get killed? Bears? Wolves? Coyotes? Mountain lions? No, they were hit by cars. They were walking alongside a road, right? So what's scary about walking in the woods at night? Well, for me, I walk into the woods as a biologist. So what's scary? Nothing. This is fascinating. When I hear a weird screaming sound, would I go towards it? Well, of course, something is really interesting there. Is it some baby being murdered by a satanic cult or something? No, it's a screech owl or something like that, but it's fascinating. I go to it as a biologist. If you play zombie hunter, somewhere in your head, the woods are not so comfortable because you know there's zombies there. And you know that's not true, but you know that you only have control of a small percentage of your brain. And depending on what you feed your brain, that's the way you see the world. So if you'd like to see the world different than you're seeing it, feed it better. Read better books. Entertain yourselves in ways that don't diminish the world for you. That's just, that's that advice from Uncle Russ here. All right, so I'll leave you. You can think about that any way you want. But someday you're going to have to give that advice to kids of yours, so make sure you think about it a little bit.